Okay, so we are now going to start the fifth section, trigonometric functions. In this section, we are going to review radian measure, trigonometric functions, their periodicity, and some basic trigonometric identities. These are the things we are going to see. Now you know, so the first thing is radian measure. Now you know that you know about degree measure. Already we have seen this in our Euclidean plane geometry. And besides that, in navigation and astronomy, we use degree measure for measuring angles. It's been that way traditionally, and it is convenient there. However, in calculus, this other measurement, this other unit of measuring angles called radians is much more convenient because it simplifies some calculations which we will come across in section 2.4, where we are going to calculate derivatives of trigonometric functions. We are going to differentiate trigonometric functions. In those calculations, we will see how radian measure simplifies things and how degree measures are much less convenient. So the first thing is the definition of radian measure of angles, and in this definition we have this diagram of a circle, which is not just any circle but a unit circle, a circle whose radius is 1, and C is the center of the circle from where two lines are emanating, which are intersecting the circle at these 2 points A and B. So we want to define the radian measure of this angle ACB, and it will be theta radians. So we will see what it means actually. So the definition goes like this: let ACB be a central angle be a central angle in a unit circle, that is a circle with radius 1 unit. Let this be a central angle in a unit circle with center C. Ideally, the definition should have said these things, that A and B are actually on the circle, but you can understand that is the case. This diagram is a part of the definition, as shown in the figure above. Let's just throw that in as well. Okay. Now, the radian measure theta of the angle ACB is defined to be the length of the circular arc AB. If you just simply say circular arc AB, there are in fact two circular arcs AB. One is this one and the other one is this one. but in the context of this definition you of course understand that we are talking about this one, and in fact to emphasize that we write theta here. So that means we have taken a unit circle and we have placed the angle in such a way that this corner of the angle lies at the center of the circle. You can view it in that way also. Say this is your angle. Now you have placed the angle in such a way that the center of the circle and the so-called vertex of the angle coincide. Then the radian measure of this angle is the length of this circular arc AP. So radian measure is the length of an arc. Now because it has been defined in this way as the length of a circular arc, it becomes rather easy to link this to the degree measurement, since the circumference of the circle is 2 pi. We know that the circumference of a circle of radius r is 2 pi r. Here that r is 1, so the circumference is 2 pi, the length of the entire circle. And one complete revolution is 360 degrees. We have pi radians equal to 180 degrees. How are we getting this? Instead of thinking of an angle between two lines as something static, that is, instead of thinking of this angle as measuring how much corner there is in between these two intersecting lines, there is another way of interpreting an angle. An angle can be thought of as measuring a rotation. You think of this line CA as static, it is fixed, and the rotation is starting from here. So in that sense, this CA will be called the initial ray of the angle, and then the rotation is like this, or it can be like this also, but just for the sake of argument, or just for the sake of clarification of this notion, let's just think that this is fixed and the other line which is rotating, which is suffering a rotation like this, is rotating like this, with one of its ends fixed at C. Then after that rotation is over, the amount of rotation is given by the angle, is being measured by the angle. You can think of the angle in that way also. And once you have that way of interpreting an angle, you can understand that you can have one complete revolution where this CA stays here, but this line, this other line CB, and hence B is a point that is moving on the circle. B starts at A, it makes one complete revolution along the circle and comes back at A. If that is your rotation, then the corresponding angle will correspond to one complete revolution rotation, and that angle in your degree measure is 360 degrees. One complete revolution is 360 degrees. But in radian measure, what will that be? According to the way we have defined the radian measure, it will then be, see here the radian measure is the length of this arc. In that case it will be the length of the entire circle. So that's why we are considering the circumference. So 360 degrees is the same, it measures the same angle as 2 pi radian measures, one complete revolution. So that is why 2 pi radians is equal to 360 degrees, or equivalently pi radians is 180 degrees. So this is your relationship between degree measure and radian measure of the same angle, okay, not of different angles. There is a potential for making a tremendous mistake here, misinterpreting this equation and simply writing pi equal to 180 without any context. This is, I should not say this is meaningless, but it is wrong. Pi is an irrational number and 180 being a positive integer is a rational number. They are not the same thing, but pi radians is equal to 180 degrees. Okay, these units must be there, then only it makes sense, and that is a true statement. Okay, now we next see the first example of this section, which is about conversion from one unit into the other. Conversions. Convert (45° into radians. To do that, we look at that relation 180 degrees equals pi radians. So that means 1 degree will equal pi divided by 180 radians. So that means you have to multiply 45 by pi divided by 180. So what you just do is, in order to get 45 degrees on this side, you divide by 180 and multiply by 45. So that means you get this 45 times pi divided by 180 radians, which equals pi divided by 4 radians. So 45 degrees is it measures the whatever angle it measures, that same thing pi by 4 radians also measures. And in the other direction, convert pi divided by 6 radians into degrees. For that you just have to do the you have to multiply by this, by the reciprocal of this, which you can make sense easily from this relation. So here what you need to do, you need to multiply this by 180 divided by pi. So that gives you 30 degrees. Okay, so that is your conversion. And in fact, there are conversion formulas. Formulas are just going to simply say that you have to multiply by pi by 1, pi divided by 180 when you want to convert degrees into radians and the other thing. But before that, there is a there are diagrams describing these conversions, which one can draw for illustrating geometrically what has gone on here. So these are two right-angled triangles. They have been drawn in such a way that those two perpendicular sides are of equal length. So these sides are in these ratios, they are equal. So by the Pythagoras theorem from your Euclidean geometry, the other one will be square root of 2 times these things. Now in degree measure, these angles are both 45 degrees, and this one of course is 90 degrees, and here in radian measure those same angles are pi divided by 4 radians as we have calculated, and this one is pi divided by 2 radians, which you can find by dividing both sides by 2. And there are two more showing the other conversion, which I am of course going to draw much less accurately than the above ones. Why so? That is because here we need a 30-degree angle, and correspondingly the other acute angle of the triangle will be 60 degree. But in terms of lengths, if one of the sides is taken as the unit of length, then this needs to be 2 times that in order to have this 30-degree angle, and the other side perpendicular to this horizontal one, that is the vertical side, then according to Pythagoras theorem should have this type of length. I mean, if one is extra careful, one can in fact make this line twice as long as this one and then make a right angle triangle, but you get the point. We are not actually doing constructions, so there is no need to be absolutely perfect geometrically. Now here this one is 30, this one is 60, this one is 90. In radian measure, this is pi divided by 6 radians, this one is pi divided by 3 radians, and this, like before, is pi divided by 2 radians. And regarding this less accurate and more accurate thing, in the physical universe there is no perfection, because there is Heisenberg's uncertainty principle. No, it will prevent you from ever being perfect. Mathematical ideas are perfect as long as they are ideas. but the moment you use them to describe something real, the moment you apply them to something from the real physical universe, these applications say, of course, a lot about the thing you are trying to describe, but all these are approximations. Now next, conversion formulas, which are just the same things written in a more formal manner. One degree is exactly equal to pi divided by 180 radians. However, this number itself is only approximately equal to 0.02. So 1 degree is roughly 0.02 radians. And when you are converting degree into radian, you need to multiply by pi divided by 180. So if you want an approximate answer, you can in fact multiply by 0.02. And in the other direction, 1 radian is exactly equal to 180 divided by pi degrees. However, this number itself is approximately 57. Well, let me just see if I have got the character. Yeah, these values are okay. There is no error in these things. And to convert from radian into degree measure, multiply by 180 divided by pi, or more roughly you can multiply by 57 also. Okay, now next we come to that thing that I was talking about while defining the radian measure. That is, there are two ways of interpreting an angle, and in fact it's the second way, which uses rotations, is the one that we are going to adopt. Of course, we have come to the notion of angles from our studies of Euclidean plane geometry. In that, an angle is like this. Now, two lines are intersecting each other. Just from the figure itself, you see that there are 4 angles. To simplify the situation, you can in fact forget about this side, so that you can think of only one angle. Actually, there are 2 angles, but just for the moment think of this angle. This angle is a static object obtained just like this, which in some sense, because of lack of a better term, measures the amount of this corner that has been created by these 2 intersecting lines. However, we have just now discussed that one other way of interpreting this angle is in fact thinking of the angle as measuring a rotation, or in fact thinking of the angle as something that has in fact itself arisen from a rotation. And in that interpretation there is one ray, okay, which you can call the initial ray. Which stays fixed. Why we call it a ray? Because it has one end that just stops there, and on the other side there is no end. That's why we are using this arrowhead. It indicates the fact that this continues on that side without any bound. And there is another ray which is not fixed and which in fact is rotating in such a way that the fixed point of that ray, in fact the only point of that ray where the ray ends on this side, that point stays fixed. The rest of the ray is rotating like this, either in the counterclockwise sense from our perspective or in the clockwise sense. After some rotation, it comes to it stops here in some position. In that position, it is called the terminal ray. This is where it has terminated, and the rotation is say counterclockwise from our perspective. So you are indicating that fact also by drawing this thing, which itself has an arrowhead. Why am I saying from our perspective? If you really think about it, we are looking at this from here, from this side of the board. For us it is counterclockwise or anti-clockwise. From that other side of the board, this same rotation will be clockwise. If you look at it from that side. In this new perspective, this is our angle, which is much more rigorous. There is an initial ray, there is a rotation that has happened, that has occurred, and the amount of rotation in fact corresponds to the angle that we will be talking about. Okay, so now there are some things related to this interpretation of angle. One thing you can immediately see from this is that the restriction that has been created by Euclidean geometry when it comes to angles is no longer available here, is no longer present here. What kind of restriction I am talking about? You see, we have always thought of angle as something like this in ordinary geometry, right? So at most, how large an angle can be? If you think of a right angle, okay, it is fairly large. If you think of an obtuse angle which is greater than a right angle, that is large, and that is larger than a right angle. But if you think of this angle, okay, in the geometry sense, so I am not using those arrows or anything, then this really does not look like an angle, although mathematically speaking it's an angle. It's an angle between these two lines which in fact are parallel to each other and are passing through the same point. So they look like the same line. But if you continue to think of your larger and larger angle, what you will then see is that you can, instead of thinking of this angle, you can think of the angle on the other side that will be larger than that flat angle, 180-degree angle. If you continue like this, the largest possible angle that you can think of by stretching this definition as far as it can go is 360 degree. However, in this other interpretation, because it corresponds to a rotation, we don't have such restrictions. You can in fact make this moving line or moving ray rotate, then again come back to this position of the initial ray, but without stopping there, it continues its rotation, and you can in fact make this rotate as much as you want. That will correspond to an angle much larger than 360 degree. 360 degree plus, if you for example make this line rotate, make this ray rotate and do 2 complete revolutions, it will then be 2 times 360 degree, and you can do this as many times as you want. So you can now understand that whatever is not possible by the ordinary static geometric interpretation of an angle as the amount of corner between 2 intersecting lines, now it is possible to have angles like this, 1000 degrees, which is meaningless here in the ordinary geometric interpretation. One more thing is there, because we have also made the sense of the rotation a part of this interpretation of angles, either in counterclockwise or in clockwise sense. We can in fact put signs to angles, positive, negative. Negative angles will now correspond to clockwise rotations. Positive angles will correspond to counterclockwise rotations. So we can have any value of angle, and that too with any sign. Now, these are some of the things that this sort of interpretation can make you achieve with angles. But now to study these angles, or rather correspondingly these rotations, you can see that this same angle you can in fact draw in a slightly different manner. You can draw that same thing like this. Say this is your initial ray, this is your terminal ray, and this is your sense of rotation in the counterclockwise direction from our perspective. And there is one more thing I forgot to say. This corner has a name. It's known as the vertex of the angle. This one is the vertex. Now if you look at these two things, and for a moment let's assume that these two are the same amount of rotation, they actually look two different things. This for one, the two vertices are actually two different points on this board. The initial lines are different, their directions are different, the terminal lines are also different, but as far as that amount of rotation is concerned, these two things are actually representing the same rotation. That's what matters, and that is what this thing has been devised to measure or represent. So it does not make sense to consider that same rotation in two different ways, and it becomes necessary to have a standard way of putting angles in the plane geometrically so that we can uniformly talk about them, and without having the risk of two different looking angles being the same. And that's where the standard position of an angle comes. That is the next thing. So from now on, whenever we talk about angles, we will always try to think of the angle as a rotation. So in this line, an angle means that type of interpretation. An angle in the xy plane is said to be in standard position. If its vertex lies at the origin and its initial ray is along the positive x-axis. Okay, so to have that uniformity, we have decided to place the angles in the plane. Once we have chosen a coordinate system by putting x and y axis, we have decided to draw all angles in such a way that their vertices coincide with the origin of our coordinate system, and where the initial lines are all positive x-axis, all coincide with the positive x-axis. Now next comes the notion of sines. Angles measured counterclockwise are assigned positive measures. Just like that, angles measured clockwise are assigned negative measures. So you can see that in this second part, where we are assigning signs to these angles, the simple geometric interpretation of angle does not make sense, because we are explicitly talking about rotations, counterclockwise, measured counterclockwise. There is no rotation involved in this simple geometric interpretation which we previously had in geometry. And two diagrams correspond to this discussion. We are now going to draw those two diagrams, one of a positively measured angle and another of a negatively measured angle. But before that, I need ink. positive measure, and this one is, the one below this is negative measure. Both these angles are in standard position. Both these angles have their vertices coinciding with the origin of the coordinate system, these two coordinate systems. And both of them have their initial rays coinciding with the positive x-axis. Counterclockwise rotation corresponds to a positive measure. Clockwise rotation corresponds to a negative measure. And now comes that thing that we were talking about, that we can in fact have angles much greater than 360 degrees. When angles are used, to describe counterclockwise rotations, our measures can go far beyond 2 pi radians. Our measurements can go arbitrarily far beyond 2 pi radians or 360 degrees. Similarly, angles describing clockwise rotations can have negative measures of all sizes. Like these angles. Some examples are given. here we are having this, of course, is the initial line, the initial ray. The rotation that we have is like this. Okay, it starts from here, comes back, and then some, and this corresponds to an angle of 9 pi divided by 4 radians. Why? Because starting from this, once you have one complete revolution, that is 2 pi radians plus pi divided by 4. So 2 pi plus pi divided by 4 is 9 pi divided by 4 radians. Like that, we have other large angles also. Another such large angle is this. Pi, another pi radians. That means 3 pi radians. And another one such negative angle, a negative measure, which is not necessarily large, but large and small, these of course don't have any fixed meaning. But it's a negative angle. Is it this what I am thinking? Oh, there are two more actually. Okay, let us first draw this one. Here the sense of rotation is clockwise from our perspective, from our point of view. Pi by 2 plus pi by 4, that means 3 pi by 4, but with a negative sign. Minus 3 pi divided by 4 radians, and like that there is this one also. So this one again corresponds to a clockwise rotation, and it is this. It starts from here, makes one complete revolution, and then continues and stops here. That means like this. So 2 pi plus pi divided by 2, that means 5 pi divided by 2, but with a minus sign. Minus 5 pi divided by 2 radians. Okay, so this way we can have angles which in ordinary geometry are they don't make any sense. there is a useful relationship. Yeah, now next we come to we are now going to, you see, we have defined the radian measure of an angle as the circular arc, or in some circle, some particular circular arc, the length of the circular arc corresponds to the corresponding angle that is there in the definition. Now this definition can be linked to lengths of circular arcs in general in any circle, not just necessarily in unit circles. So that is the next thing. There is a useful relationship between the radian measure of an angle, or the length S of an arc AB of an arc AB on a circle of radius r. And the radian measure theta of the angle that AB subtends at the center C of the circle. So the situation now is this. There is a circle some circle of radius. I draw so bad circles, but anyway, what can I do? So this is a circle of radius r, and in it there is an arc, circular arc AB. So let us call this circular arc AB, which has length S, and let's just join these two things. So this is the center C of the circle, and the angle that this arc subtends at the center, that angle is theta radians. The radius is r, so CA is r. But now what we do, we draw a unit circle with the same center. And let the points, these points, be A prime and B prime. So this CA is 1 and this much is R. CA prime is 1 and CA is R. And you know that this circular arc A prime B prime has length theta, because that's what it means for this angle to have measured theta radians, and this is a unit circle. So we should remember that this length of this smaller circular arc is theta. If we draw a unit circle with the same center C, the arc A prime B prime cut by this angle, on this unit circle will have length theta by the definition of radian measure. Now, just like we have the notion of similar triangles whose angles can be put in a one-to-one correspondence so that corresponding angles are equal. They are similar triangles, and similar triangles have the property that the corresponding sides are in the same ratio. So just like that, there is a notion of similar circular sectors. These two circular sectors, A prime C B prime, this sector, and A C B, these two are similar because the angle, both of them have the same measurement of angle. So they are similar, and that's why they will also have that similar relationship that two similar triangles have, that is their corresponding sides are in the same ratio. Here also corresponding sides will be in the same ratio, although two sides are actually curved sides, they are not straight line segments, but that's the same thing happens here also. So the authors write, from the similarity of the circular sectors ACB and A prime C B prime, we have this. AB divided by AC is equal to A prime B prime divided by A prime C, and AB has length S divided by AC has length R, equal to A prime B prime has length theta and A prime C has length 1, or S equal to R theta. This is a relationship between the length of this circular arc, the radius R of the circle, and the Radian measure theta of the angle subtended by this circular arc at the center of the circle. You should understand that here, the way we have drawn this diagram, our r is greater than 1, but r can be less than 1 also. In that case, the unit circle that you draw will lie outside. It will have the given circle inside of it, in its interior. But r can also be equal to 1. And in fact, when r is equal to 1, we get the special case that we have already seen in the definition of radian measure. When r is 1, s is equal to theta. So that is why s is the radian measure of this angle. In fact, that's how we have defined radian measure. So this is the general formula which is true for any circle. And this next remark is important. Notice that these equalities, that is this one or this one, same thing actually written in slightly different manner. Note that these equalities hold precisely because we are measuring angles in radians. Because the radian measure has in its definition an arc length, that's why these very convenient relations work. The degree measure also is related to geometry. What is the degree measure, by the way? What is the definition? What if someone asks you define 1 degree, what would you say? Your simple definition would be just this: one complete revolution is taken to be 360 degree, okay, and 1 degree is 360th part of that. It's just that. But you can see that this is not as intimately related to the geometry of the situation as radian measure is. Looking at this relation, such relations don't exist there for degree measure. I mean, using this you can, of course, you can change this theta into degree measure, but that is not something fundamental about the degree measure. It is coming from radian measure and it does not serve any purpose actually. Radian is that's why much more convenient to work with when at least we are in calculus, and that is why we have this next angle convention, which is just simply use radians. More specifically, from now on, in this book, in this text, it is assumed that all angles are measured in radians. Unless stated otherwise explicitly. Unless it is said, it is mentioned before a discussion that the measurement of angles will be done not in radians but in degrees or some other measurement, we have to assume that the measurement is in radian. And in fact, you have noticed one thing. When we were drawing those large angles, we did not write anything beside those values. Minus 5 pi divided by 2. I said, when saying those things, I said radian, but the authors did not write anything. So that is coming from this convention, because the measurement has been assumed to be radians, it's fixed. Radians, unless degrees or some other unit is stated explicitly. Is stated explicitly. When we talk about the angle, angle pi divided by 3, for example, we mean pi divided by 3 radians. Which equals 60 degrees, and for example not pi divided by 3 degrees. That does not mean that pi divided by 3 degrees is meaningless. Pi divided by 3 degrees is also a measurement of some angle in the unit degrees, where the value is pi divided by 3. But usually when you see things like this, and when it is mentioned that it represents an angle, the unit is radians, that's all. And this is also very important when you do calculus. Keep your calculator in radian mode. If you start using scientific calculator for doing calculations in calculus and elsewhere in mathematics, you will see that when you are using trigonometric functions, there are keys for those functions in those calculators, right? And in fact, if you look in your smartphone, you have the calculator app. In that calculator app, if you look carefully in the options, you will find that there is a key to toggle between ordinary calculator and scientific. You will get keys for the trigonometric functions there, and you will there also get one key, in fact 2 keys I think, for that degree radian preference. Which one do you want to use as a unit of measurement for the angles? There the authors are advising us to keep the calculator in radian mode in that part for calculus calculations. And based on this on that relation S equal to r theta, we have this example 2. It also comes in the form of a question. Consider a circle of radius 8. Part A asks this: asks us to find the central angle. Subtended by an arc of length 2 pi on the circle, and there is this part B also. Find the length of an arc subtending a central angle of 3 pi divided by 4. That means 3 pi by 4 radians according to our convention. So the solution is this. The solution to A, we have to here find the arc length. That means, no, we have to find the central angle. So we need to find theta subtended by an arc of length 2 pi s divided by r. So s is 2 pi and our radius of the circle is 8. So the angle it will subtend is pi by 4 radians. And in B, I think we have to find arc length. Yeah, subtending an angle, central angle of 3 pi by 4. So that arc length is S. S is equal to R times theta. R is 8 and theta is 3 pi divided by 4. So the arc length is 6 pi. After this, we have the definitions of the trigonometric functions. Now in the trigonometric functions, you can see that we already have a much larger room for defining the trigonometric functions, because our definition of angles has been extended from those small angles given by ordinary Euclidean geometry to arbitrarily large angles, that too having signs and everything coming from that rotation interpretation. So our definitions of the trigonometric functions with which we are familiar from that, the right angle triangle definitions that we already know, that thing will now also be extended to accommodate these large and arbitrary values of angles, and that too even negative values of angles. So this definition that next comes will be new, and the old definition will be subsumed in it. When we actually get to those small angles, we will see that the new definition reduces to the old definition. This, however, we will see in the next calculus video, and then we will go to the other things, periodicity of trigonometric functions, their basic identities. We will see that even with this new extended definition, those same trigonometric identities continue to be true. Even when your theta, for example, is a very weird angle which looks like this, minus 10,000 say radian. You can think of degrees also. Minus 10,000 radians will be some very large negative degree. In degrees, it will be some such value. Even with this value of theta, it is still true that sin square theta plus cos square theta is equal to 1. We will see these things, but now because our angles are not like ordinary geometry angles coming from ordinary geometry. The meanings of sin theta and cos theta will be something new. So we will see these things in the next calculus video. So I am ending the video here itself. Today is Tuesday, no? So coming Friday we have already gone through vector spaces. So coming Friday we are going to see number theory again, and then graph theory. So it will cycle like that as usual. So that being said, this is all, and see you next Friday. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.